Um, yes. So, in addition to the requirements from the building envelope and air tightness and energy calculation, we also need to look at energies. Yeah, basically, we have to look at different kinds of things, and in some cases, when we have other buildings, like specific buildings, you have like, let's just say you have some kind of production, or you have some kind of specific building that will use more energy because they have more requirements for energy. So how do we deal with that? So basically, in general, you could say that the energy calculation that will a supplement to buildings is giving to buildings which have more than requirements of 300 lux, and this is lux is a measurement of light intensity, how much light is coming on your table when you're doing work. And in Denmark, the minimum requirements for most of the buildings, typically normal type of work would be 300 lux. But if you have like an architecture office, a lot of the work is requirement is 500. And in that case, the building will use a lot more energy on artificial light. And then there's are giving supplements. I mean, basically, the energy calculation could extend the minimum requirement a bit more. And now I'm going to give you a specific case of where this could happen. So if the light requirement is for the building is above 300 lux, you get extra your energy calculation will be higher than the requirement. You have a ventilation system that is needed to this second area during the heating season for atmospheric indoor climate. And basically, this could be an auditorium or a big lecture hall, for instance, or a cinema or something like that. Basically, places where people are really sitting really tight, and there are a lot of people per square meter. You will have a requirement which is above 1.2 liters. And in this case, you can also get addition or supplement to your energy calculation. If the hot water for typical buildings or what we specified as other buildings like offices, if they have a hot water consumption above 100 liters per square meter for the heated floor area. So basically that could be a swimming hall, a place where you go for swimming, etc. You probably have, or basically it could also be it could be a sports institution or sports place where you do sports, where a lot of people will take a shower. This number will probably be bigger than 100 liters per year, and then you could like get supplemented energy frame. If the service life is of 45 hours a week per day, if it's higher than that, you can get an extra supplement. If the ceiling is above 2.8 meters, yeah, so basically these are all referred in this SBI instruction book that I showed you earlier online, 213. You can see some further details. But basically the things that I 300 lux, 1.2 liters, 100 liters, 45 hours, this is the general, or this is the normal building you do for an office building, etc. We're going to calculate, but if for some reason you're working with a specific type of other building which exceeds this, you get supplemented energy. So basically that's what you should include. Yeah, so if you need to get the program, the 18, I should you, yeah, I'll show you. So if you don't already have the program, I'll show you how to get it. So basically, by opening this, yeah, the presentation I showed you earlier, you can see that this is where where you can get the program installation of BE18. You can use this. I'll just open the instead. So basically, you can get the program by opening. Why can't I open this? Okay, webcam. I'll open this file and then I can access the link. Yes. Okay. So if I go to this link, you can log on here using these informations. Basically license number and code, and when you log on, let's try it. Doesn't work. Okay. Oh, this is the old one. Yeah. Find the new one. Okay, I need to update this information. I can see that. Okay, I'm sorry about that. Because so this says 2019, which is not right. It should be 2021. Well, anyways, we'll look into that. Yeah, basically. Okay, I'll find the newest version information for this one, and I'll send it to you after this lecture. I don't know why I did not put that. So basically, you can log in here and you can just download the program. And when you download the program, you will get this installed on your computer. So basically, this one is in when you open it, it's going to be in Danish. But you have so basically when you start it, it's going to be in Danish. But when you start it, you can always go into show piece. It's a Danish for show, and it's language, and you can say English, and the program will be in English from now on. So every time you open it, it's going to be in English now. One function which is really nice when you're looking at this is F1. If you press the button F1, you're going to get some help. But as you can see, it's in Danish, and as far as I remember or know, it's not going to be in English. I don't think you can translate this one into English, which is unlucky because it's interactive. So basically, if you need help with this part, you can just press it and it's going to explain to you how to get some kind of help with it. So you can always put this in Google Translate or whatever. But that's why I showed you this earlier. Let's see here. This one, energy needs of buildings, basically part 2 calculation, which is basically this function, F1 function. So if you need help with this program, you can go to part 2 calculation, and you can see how to actually answer some of these parts, or what to fill in. It's going to be described in this one. So basically, unit area, what does that mean? Unit basement, gross area, second floor area, and etc. And when we come to ventilation, which we'll talk about later, it will be described here. Okay, so this is something that will be really nice for you to access the SB instructions for 213. Remember, you need to do this translation to English because basically it's in Danish, but you can actually get it translate to English. Okay. Yeah. Basically, that's what you. So what does this program do? Basically, it makes a calculation of all the energy added to the building, all the energy added to the building, like the sun, how much energy is getting added throughout the year by the sun, how much energy is getting added by the people, by applications, not applications, basically equipment, light, and from the ducts, basically ventilation. How much is getting in by the heating, how much is getting out by cooling, by mechanical ventilation, infiltration, uh, heat transmission loss, like heat loss. So basically, this is what the calculation does. And also, it has like an extra. So basically, if the calculation finds out that we're not cooling enough in the building and the temperature is going to exceed 26 degrees, it's going to remove that excess heat by a kind of inefficient cooling system. So you're going to get like a punishment, you could say, if you don't have enough cooling in your building. So basically, if that happens, you should either find out why we're getting so much energy into the building. It could be through the window of the sun, so we could start blocking out the sun, or we could increase the cooling system or ventilation system. Yes. But basically, the program will do a calculation of all these things. So basically, transmission loss and ventilation loss will be the heat loss. And when I say ventilation, it's both the mechanical ventilation, but it's also the infiltration part. The transmission is through the envelope, heat loss through the envelope. Heat gain, internal heat gain will be people and equipment, and solar incidents, basically radiation from the sun through the window. Heating and cooling requirements are calculated from heat gains and heat loss. So basically, you could have a winter time, you could have a lot of heat loss, but also some heat gain. And then the total consumption will be some, the heating system will start heating in order to keep the temperature of 22 degrees. But at the same time, in the summertime, you have some cases where you have you don't really have transmission loss because it's hotter outside or it's almost the same temperature as inside. So this will roughly be zero, but because you have a lot of sun and you have a lot of people and equipment inside, appliances or equipment inside, you actually get too much energy with the building, which will result in the temperature rising. And if it's too hot, your ventilation system will cool down, and then you will use energy from electricity for your cooling system. So basically, this is something that this program is calculating for us. So what are the low energy strategies for actually preventing this? Location of the windows are probably really important because placing, at least in Denmark, placing a window, when you're north of the hemisphere and this far north as Denmark, placing windows in the south direction towards south, the South Pole, will actually be a place where a lot of sun is going to enter the windows. If you place them in the north facade, the sun is not going to get pretty much direct. Basically, there's almost zero direct light, which will also decrease how much energy is going to get through the windows, which can be good, or it could also be bad. location of the windows is also really important. Also, I would say the location is gonna, if it's gonna be with the 90 degrees to the horizontal part, or is it like parallel with the horizontal part or somewhere in between, has also some meaning. Building orientation is also important. Building geometry or form is also something that you need to do with it, especially if you have a long thing, probably have a lot of energy. You have more facade, or if you have a compact building, you have a less facade and less energy loss, and etc. Heat capacity of the construction. So basically, you see this construction is built of a heavy equipment, or heavy materials like concrete. Concrete has a very high heat capacity. So basically, that means when we have really hot days in Denmark, nothing compared to Vietnam, but if we have hot days in Denmark, heat materials of construction with high heat capacity will have the capability of storing the heat energy in the construction, so the air in the room won't get that high. And during the cold nighttime, colder nighttime, it can actually give, or the heat will exit the construction. This will like dampen, you could say, the temperature raise and temperature. Basically ensuring that temperature is too high during the daytime and not too low during the nighttime. For the winter time, this is probably the opposite. So basically, when you want to heat up a room, it's gonna cost a lot of energy, because you also need to heat up the construction. But on the other hand, if you have like wood or something that is really lightweight, the air within the construction is going to get faster high, and then you need a cooling system in order to get the air out. So basically, the heat capacity of the construction should help us here if we put some materials that have high heat capacity. Yes, energy efficient windows. So one thing was the glazing of the windows, but energy efficient windows could, in some cases, could mean that they're really good at preventing sun from coming into the buildings. If it's a building that has a lot of heat cooling demands, but if it's a building with low cooling demands, it's actually picking windows which have the capability or properties to access and letting the energy go into the buildings. So this is something we have referred to as the G values, solar transmission efficiency. And there's energy efficient ventilation. What is that? We'll probably talk about this tomorrow. But in short, the bigger ventilation ducts you can have, the shorter the ducts are, the more efficient. And of course, there's something with the type of ventilation system you have, but you can also do this. Solar water heaters you could use, and photovoltaic solar cells. Basically, the last two parts, it's something I would call, personally call blue on green solutions. These two won't actually do that. It won't solve the heat, the energy consumption of the building. It will just do so. Blue on green solutions. Energy consumption just being reduced by a sustainable energy production. If you ask me, it will always be better to reduce the energy consumption than to actually produce your own sustainable energy, because the reduction of energy consumption will be better for the environment than actually just having high energy consumption and solving it with the solar cells or solar water heaters. Okay, so I'm gonna go quick through some of the things here, because we also need to talk about the part of the. So basically, This is something that you probably talked a bit about last year, and I will go through it again. And the next presentation will be more about the technical services in the building, whereas this one will be about the building envelope. So this is the main site for the building, the energy frame. So basically picking what kind of building we're looking at, what is the floor heated area. And again, if you want some kind of help, you can always go into press the F1 button, or you can just use the SB instruction book 230. Yeah. So, and also normally in Denmark, heat supply is something we'll discuss here. But normally in Denmark we would use district heating, remote heating, or yeah, we have many words for it. But in this program we call it district heating. Yeah. So basically, by pressing F1, and we have this thing called heat capacity. This was the old way of doing it. If it was like light building, middle building, or light weighted building, middle weighted building, or heavy building, these were the numbers you could use. But today we will look into a different path. So today, if you look into how much heat capacity of the building, what the heat capacity of the building is, you look at the ceiling, and I think this one is in Danish, so I think I will jump to the website. Just give me 1 second, and you can see what's. So basically, in order to find this, you need to translate this to English, which I already did. And we go to main data. Heat capacity. So basically, this is what I'm talking about. So, how do we find out about this heat capacity? Basically, this is the table that I showed you before on my PowerPoint, but now it's in English. So first off, we'll look at the ceiling. What kind of ceiling do we have? What is the most inner surface of the ceiling? What is the most inner part of the floor? What is the most inner part of the exterior walls, partitions, inventory? So basically, this is like a really simple calculation. Here we have an example of a detached house with the area consists of walls and partitions as well. So basically, if you look at that, the first one is the suspended ceiling will be 3 concrete, and the next one will be clinker concrete. If we have this example, it would be 17, and etc. So basically, adding all those numbers together, the result will be 55. So basically, that will be what we'll put in. So basically, in other words, the heat capacity of the building will be 55 watts per hour per Kelvin per square meter. Okay. So going back to this presentation, this is the example of before, as you can see here with the red. So basically, you look at the ceiling, the floor, the exterior walls, the interior walls, or partitions, as they're also called. But for your project, of course, you use the materials that you actually have had. Yeah, one thing you also should look into is the building compact. It's like if the building is compact, or if it's not compact, is it small or somewhere middle or big, and also the room sizes are the small rooms in between or big rooms. And this is all relative things. So how do we look into that? And basically, there comes a bit help from the instruction book 230. You can actually calculate this number, small, medium, or large, which depends on the compactness of the building. It is an outer wall area respectively to floor area. So basically, if you have a lot of outer wall area compared to floor area, the compactness of the ground, that the outer wall area is small compared to the floor area, you're going to have a low compact area, right? And the same with the room sizes, the small, medium, large, corresponding to 2, 1, or 0.6 square meters. So basically, how many partition area wall per square meters. This is something also you can calculate, or you can just evaluate depending on the types of. It says like here, small rooms are typically homes, while large rooms would be rooms of classrooms or offices. Okay. If you have some question during the presentation, you can just add them to the chat, and I'll try to answer as good as I can. So, design transmission loss. Basically, that means the worst case. So this is how we design our heating systems. Is calculated like this. I don't want to go too much into depth with that, but it has, of course, something to do with the U value and the area that we're looking at, and the B factor. The B factor is basically the B factor is something that is telling us if the other side of this construction, this building envelope structure, is it outside on the other side, or is it something else? And something else could be the ground, could be an unheated garage, could be an unheated staircase, or something like that. Because this is the way, using these B factors, this is the way of telling the program that what is happening on the other side of the wall is not like minus 12 degrees, it's probably something a bit higher. Because if you have like a room besides the building which is not heated, any heat loss or the temperature on the other side will not be like the outside temperature. So when we look at the climate envelope, what we need to take into account is area of the specific wall. What is the danger here? So here we have the area, and if you change the language to English, it will also be so basically this will be the parts like the exterior wall, roof, floor, the area, and the value. Then you have the temperature. This one is energy, and it's also really useful the dimension part. So basically, if you don't drive by anything here, it's going to think that or it's using it don't drive by how the temperature is. If you don't have to make it the outcome, you just find out obviously the worst case. This is the same thing as heat loss. So this is so that factor, what is to consider there? Basically, if it's as a standard, it's 1, and if the temperature factor is 1 in most cases, basically, if the external side of the building is outside, it's going to be 1. So basically, if you have a wall where on the inside it's 20 degrees and the outside is it's basically just the air from the outside temperature, it's going to be 1. But in all the cases where this is not the case, this temperature factor should be different. For instance, this one on line number 3, it says 0.7. And basically, it's because either the temperature factor is 0.7 because we have ground decks without floor heating. So basically, meaning that we have ground floor, and underneath the ground, there's going to be ground, there's not going to be air. So the temperature factor is going to be different. And setting to 0.7 basically means that it's going to take into account that the temperature on the ground is different. That it's going to follow. It's going to be how to say close to the outside air temperature, but it's going to be more persistent. Basically, meaning that if you have like an air temperature of minus 12 degrees for a couple of hours or a couple of days, the ground temperature underneath the building is not going to be minus 12. It's going to change really slowly, and this is basically why we have a lesser heat loss through the ground floor. And there's other examples of this floors without floor heating and etc. When we're measuring our building envelope, we have to look into DS418. I already made this document, the standard canvas, the file sharing area of canvas, so you can always find it there. Basically, this you can always read this afterwards. But so basically. The way that we measure it is if there are two types of building or way to construct not only two, but two ways to could be done. Or if you have like a hot roof where the roof is going to be heated, or you have one where the roof is not heated. So basically, you should always follow the insulation. And as you can see, it's always like the brutal areas. So basically, we include the exterior wall and we include the upper part of the construction of the attic or the ceiling. The same, you stop at the top of the wall and you go all the way. If there's an unheated basement, all the way to the bottom. If it's a heated basement, you only go measuring from the top of the floor as well in this part. And when we measure the floor, depending on if there's a ground underneath, we're going to measure from the inner part of the wall, and if there's unheated basement, it's going to be from the outside part. Okay, so if it doesn't make sense, just why it's like this. There's a long explanation to why it's like this, but if you follow these instructions, you're going to do the calculation properly. This is how you will measure the areas. So basically, when you put in the areas here, this is how you should measure it. So basically, also going back to the temperature here. So what kind of temperature? In most cases, it's going to be 20 and minus 12. But what about the cases which this is not true? So basically, we're assigning temperatures when we're designing our heating system. We say that it's going to be, in the worst case in Denmark, it's going to be minus 12 degrees outside and 20 degrees inside. But you have some certain cases where it's going to be different. For instance, behind this heating radiator, it says 50 degrees. In praxis, this is basically if you have an uninsulated wall on the other side, which often is not the case. Normally, not the case in Denmark. For newer buildings, for older buildings, this is often happening. For example, in the building I'm living, there's no insulation behind the radiator. And also, if this radiator is, if there's a window behind the radiator, you should also use 60 degrees. If you have a basement which is not heated and it's ventilated, every basement is going to be ventilated. If this is the case, you should use the temperature minus 2 degrees. So basically, between the construction area, this will be 20 degrees and minus 5 degrees underneath. If you have a heated basement, it should be 20 degrees, like in the rest of the building. And underneath the floor, it should be 10 degrees. And there's like a temperature if you go from 0 to 2 meters underneath the ground for the wall of the basement, it should be minus 12 degrees. Underneath the 2 meters, it should be plus 10 degrees. Okay, I hope this makes sense. And the last part is if you have floor heating, everything that is connected to the floor heating is going to be 30. Um, if the floor, if this is heated underneath, this doesn't really matter. But if you have floor heating here in the basement, and if you have 10 degrees underneath, that would then you should calculate the floor as 30 degrees, basically because the floor with floor heating will have a temperature of the floor will have a temperature of 30 degrees, not like 20 degrees, and that's why the heat loss will be higher. I hope this makes sense for you. Okay, so you're okay.
May I ask a question?
Yeah, sure.
What is counted as a heated floor area? For
Yeah,
example, like if I have ventilation going inside my house and also insulation in my wall, and but a floor heating system only in some room or some part of the house. Uh, so what is counted as heated floor area?
heated floor area. Yeah, that would need to be okay. I'm not sure I totally understood your question, but I can say I could if you have ventilation system running. Could you ask the question again? I didn't need to hear that again before I answer.
Yeah, I was just wondering that if I have ventilation going inside my house, does all the floor inside my house counted as heated floor area, or just the one that have the floor heating underneath is counted as heated floor
Yeah,
area?
yeah. You should only use the 30 degrees in the actual area of the floor that has floor heating. And now you asked about the ventilation. Normally, the floor heated area would be in Denmark. It would be a water system, so basically like pipes with hot water. So I wouldn't really mix the ventilation and the heating pipes. I don't know if that answers your question.
So when we put in a number in the B18, they
Yeah,
ask for the heated floor area, and
yeah,
I'm just putting the area that I have floor heating underneath.
yeah,
Is that right?
exactly.
Okay, okay.
Yes.
I got it. Thank you.
Yeah. Okay, and I don't. I'm not sure. I'm exactly know how to answer to pronounce your names, but is it Quan? You don't have access to that book. Um, have you? Okay, I think maybe. I think I need to look into that. Do you have access to our library when you're studying in Vietnam? The reason why I'm asking that is because the reason why I'm probably getting access to that is because uh, I'm on the school network, and okay, I will ask Raymond or Carl, sorry, Redmond, regarding if you have access to our school library. Because if you have, you can do this VPN connection, and when you have that, you have local access to our school, to the internet, and then you'll have access to that part. Yeah, or else we need to. Yeah, you can find the book on Canvas as well, but I'm not sure that it's in Danish or English. The one on Canvas. Oh, it's an English version. Okay, that's nice. I didn't know we had that. Yeah, but I will just note that we have version 6 for on Canvas, and the one that we're using now is version 6. So yeah, okay. So I'll show you. That's a good question. So great that you actually asked the question there. So on Canvas, you can find the SDI directional instruction for 230. It's version 4. And that's the latest one. But the one I found online. What was this version? Basically, what it means is that these are what the used updates, version 6. And every time, so basically, if it's the too old version, the way we used to calculate heat capacity will be a different way. And if it's a too old version, older version, I'm not sure that you actually can calculate it. So what I would suggest is that when you read in the book, you use this one. But when you're actually doing the calculation, just press F1 or the question mark. No, not question mark. It's F1. I think it's the help button. Isn't it here? Yeah, help. So basically, if I go here and I want to know something about the U value or a temperature factor, I'll just press F1, and you can use this one and see the actual number. See if it's the same in the actual book, because basically what you read here should be the same as what you see in this one. But since this is the version 4 and this is version 6, some updates in the numbers will probably be there. We'll figure this out as we go. Okay. I think that makes sense. Okay. All right. Yes. So basically, calculating the U value, this is something that you probably done before last semester. When we come to linear losses from the foundation and around the windows and etc., it's basically the same. We have the length, we have the linear loss factor, and we have the temperature factor. In case of floor heating, we should correct the floor for even though it's if there's a slab, it should be 1.0, but if there's actually if there's floor heating, you should have 1.3. So that's, you should also take this into consideration when you have floor heating. Linear loss, basically it's looking into DS for 418. You can see tables regarding what kind of number you should use depending on what your construction looks like, or you can find some things on the internet. Basically, what the linear loss means is that there was the easiest way for heat temperature to exit will be going directly outside instead of just going vertically or horizontally. So horizontally or vertically, the heat will have an easier way to exit this through your concrete foundation or whatever material we use there. We can also find some numbers in the EasyOver catalog. They have some numbers, because as you can see, according to the Danish standards, the heat loss of the foundation should be calculated in a dynamic program such as heat. This is something that we will not use time on. It's a bit complicated, but EasyOver, who's actually selling some of these materials, they have done some pre-calculations in a table, like in the DS418, and we can get some information from there. So basically, if you go to their either Leica or something like that, they will choose some kind of presentation of how the foundation is done, and then you could see some kind of what the U value be. Some of this information I already put on the links or PDFs I put on the canvas. And again, you can also get some solutions from Xpan, which is another company producing them. Linear loss around the windows from Melfac. They also did some kind of pre-calculations. So if you can't find the ones that are used to the ones that are actually in DS418, the tables in that one, you can see what information they have. And most of these websites also have international access, so you can also get this in English. Yes, so basically when we're in the third area for the windows, there's a lot of things we need to look at. Basically, there's like two ways. Either you can say how many windows you have and what is the size of that specific window. Or sometimes I've seen someone just say once, only setting once in the number, and then just say the total area in the other one. But either way, it's going to give the same results. But I think setting the proper number will be an easier way to do quality control or quality assurance of your work. So orientation, these are in relation to Danish corners of the world. So V is west, and N is north, U is basically east, S is south. But you can also put in numbers. So basically, I'll show you. So when we're doing the table, sorry, you can also put numbers in. Basically, this one says the orientation. It can be like from the compass, north, south, east, west, or somewhere in between, northeast, etc. But you could also use degrees, so from 0 to 360, which is a whole around the circle. So 0 degrees is north, 90 degrees is east. So basically, minus 90 degrees will also be west, or you could say 270. So instead of using the letters, you can just say north, that was 0, 0, 90, minus 90, 70, 70. Basically, this will give the same result as before. And the fun part about this, I wouldn't say fun part, if you're good at Revit or some similar program, you can actually get the orientation in degrees, and then if it's like a random, like let's just say 50 degrees, you can just add that number. So I would suggest using numbers instead of orientation. Just keep in mind that when we're doing the orientation, that 90 degrees is positive, is east. So we're going clockwise while we're counting the not counterclockwise. Okay. Yep, let's continue our presentation. Oh, sorry. Slope of the window. So basically, if the window is on the facade, it should be 90 degrees. If it's on the roof is flat, it should be 0 degrees. And if the roof is like with a slope, it should be somewhere in between the 90 and 0. Area, yeah, basically the area of the window. This is including the frame of the window. So when we're talking about windows, it's the glass itself and the frame glazing. And what is the U value of the window? The temperature factor. This will typically be 1 because most of the windows will point towards the outwards air. The air temperature or the air temperature for the outside world, but in some cases you could have a window turn into unheated storage area or something. In that case, you should change the temperature. This one is going to be calculated automatically by the input you put in. The FF factor is basically how much part of the window is glass. So the part which is not glass would be the frame part. So basically a factor of 0.8 means that 80% of this 1 square meter will be glassy, where the sun can actually pass through, where 2%, 20%, 20% will be frame, which will only have a heat loss. Okay, that's the frame. And we have the G value, the sun transmission factor, basically saying, well, of this total glass area, in this case, 70% of the sun actually hitting or hitting, reaching the window will get through the window. The rest of it will be like reflected out towards the world again. So again, the lower this number is, the more sun we reflect out of the window. In some cases, that's a good thing. In some cases, that's a bad thing. And then we have the shadows. Where we define the shadows is in the next one. But if we have a shading, we should go. Shading basically means if we have one, in this one we don't have any shading, and if we have 0, none of the sun will actually get through. And this is something we get from the manufacturers of shading producers, manufacturers. So basically, depending on if we have internal, external, or inbuilt shading system, is it automatically being used, or is it manually controlled, or automatically controlled? Also has an effect. And all these factors is something that we get from the producers or manufacturers. Yes. So, yes, so solar radiation through the window. The G value, these are just some values that we found, random values. If we have 1 layer glass, it's 5.9. If it's 2 layer glass, it's typically 2.9. These G values, these are just examples of what it could be. But in order to actually fit, this is from a source, to actually know what the value is today, you should go to the manufacturer of the window and get the values. But these are like some examples. The FC factor, as I told, is the shading factor. It describes how much solar, what is coming through this solar shading. It's like something happened to my There are also some interesting, again, some from this source of the book, Instruction 202. So then if we have a 2-layer glazing, or if we have external shading, internal, vertical blinds, roller blinds, what will the factor, sun shading factor be? B80 for the sun shading factor. The FF factor, which I told you about how much percentage of the window is actually glass. So when we push it, when we do the area of the when we do the area of the window, we should put in the whole area, including the frame. But also, the manufacturer will describe how much part of the actual window area is actually glazing. This is something you also see. In this case, if it's a big window with low frames, it's going to be around 90. If it's smaller windows with the same concept, it's going to be higher because the area ratio between the frame and the window is going to be lower, and the total area, the factor or percentage of glazing will be lower. And if we have these traditional windows, which we have in Denmark, it's going to be pretty low glazing. So these windows are not particularly good. But, a lot of people list on the only old Danish tradition. So a lot of people like them architecture-wise. So they still use them. Yes. So this is just an curve describing heat demand for windows depending on the orientation and also the slope of the window. I think you can use this for basically to see how much energy it's going to lose depending on how much energy we're going to get in. Maybe get some insight. So the shading factor, which we will look into now. These are so basically FC factor is if you're shading from active or manually shading, but the shading in itself, it's basically the fixed things like the neighbors, like the if a part of our own building is shading our own windows, or if we have some kind of part of it hanging out, like a balcony or something, is going to shade or some of the windows. We need to define this. This is also going to change. It's going to affect how much energy is going to get into the building. Yeah, so this is something we need to look into. And basically, for the horizontal shadow, it's basically angles we put in. So we look at the middle point of the window and what is the, so basically this is like a triangle. And we look at what is the angle of this one. And the higher the angle this one is, for especially in Denmark in the winter time, the sun is really low. This building from the neighbors will probably, well, not probably, it will affect how much sun is going to go into the window, especially if this is in the floor area and if this is a lot of stores. The higher up we get, the more sun is going to get through. So we need to define this. We call it the horizon angle. And if you just put in an angle, the program will calculate how much it means in relation to sun factor. Then we have an overhang. This could be from a balcony above. It could also be from the roof. If we have a roof overhang and this small angle here, we also need to put it in. And then we have the left and right shadow. Basically, if this building is like shaped like an L or something, this window is going to get, if this is the east, this is where the sun goes up in Denmark, and it's going to go around to the west during the day. So if we have an L-shaped building, this part of our own building is going to make a shadow for this window. Okay. And then we have a hole in the window in percentage, basically how far out is the window depending on the width of the window. And this is a calculation like the X factor over the Y factor, and it's a ratio. So basically means that the farther back the window is, the more these corners are gonna make shadow for the window. And in that case, less sun is coming in. But if we have a window where it's on the facade, it's going to be basically zero above a number, which is in other words, a lot of sun is going to get into the building. So I brought some pictures from some like this. I don't know what I did. It's like this presentation. It's zoomed in. I need to just give me 1 second. No, didn't change anything. Okay. Um, so basically, this is this is just some examples of overhangs. You can see that it's going to be this window is not going to get a lot of sun from above, not directly sun, at least in this one as well. But this one gets more because this overhang is not that big. The reason why we built it like this, there are a couple of reasons, but one of them is protecting the facade of these corners from rain, so we don't get rain into through this connection here, construction connection. This one as well, protecting these areas from rainwater, but it's also gonna do some kind of passive sun protection from the sun. You can get something like this for these windows on the roof. They're really effective at closing off sun if you have too much sun. Then, yeah, those are some examples. We have this thing called unheated room. I would suggest not using it that much. Basically, if you have a garage that is unheated, or if you have an outside living room or which is not unheated, this is just some examples. Or have a storage room which is not unheated, you can calculate what the B factor should be depending on what the room looks like. But it's always an option just to pick the number 0.7, and I would suggest doing that in order to do the calculation more quickly. This is like overdoing it, I guess, because even the instruction book says we can always pick 0.7. The only reason I've seen the examples of where we haven't used it and actually done this calculation was in some cases where it actually had a big effect on the energy calculation. And since the energy calculation was really close at being above our minimum, we did the calculation and it actually saved us something. So that's why we did it. But I wouldn't suggest looking into that. Yes, so there are some references. I think I also shared on Canvas. So I would suggest you guys looking into it for some, yeah, basically for getting some numbers for this part of the calculation. Okay. Yes. I will take a 3 minutes, 5 minutes break, and then we'll continue with the next presentation. Okay. And then we can start with some questions maybe. So I'll be right back. Okay, I'm back. Just 1 second. Yeah. So my next presentation, well, this class will continue for roughly 35 minutes more, 20, 34 maybe. And basically, this is the first time I'm doing this lecture or online or to Vietnam. So I actually didn't think it was going to take this long. So I'm just going to use get as far as I can, and then I think I will continue tomorrow because this PE18 program is probably the most important part that I should teach lectures in. So that's why I'm going to focus on doing this thoroughly and doing it properly and use most of my time for that. So I'll continue from here. Okay, so I've opened the next presentation, energy calculations in PE18, and basically now we're going to talk about the inflation part, whereas before we talked about the building envelope. But before I continue, is there anyone who has questions regarding the stuff that we talked about so far? If there's, in my experience, some of you guys will probably have some questions when you start doing your own calculations. And then I think, yeah, so when you start doing your own calculations, you start having some questions, and I think you should just ask, so when you start doing your own calculations, the question will start arising, and I think we should just, we should take questions later when we have our what can I say? So later in class, you have set some time for supervision. This is basically somewhere apart from questions. So again, before the other one. So basically, earlier I showed you this presentation. I have no idea why it's zoomed in. That's this much. It's something, but basically, in week 46 and week 51, we have we're gonna meet if you want, and I think you can ask. You can in that point of time you probably already done some calculations and you probably found some questions, and that's probably the time for us to discuss it. Maybe at week 44 as well. Okay, so you can write down your questions. You can email them or something, and I'll try to pick up the questions. If you have some questions for week 44, that's also fine for me. So we can take some of them there. But basically, as I understood, you're supposed to do this calculation of PE18 energy frame during your project this semester, and I think you should start doing that as soon as you can. According to your project, because I have no idea where you're at right now during your project, but at some point you'll have to do this program. This will be 18 calculation, and then we can meet again at this point at these dates, and we can take the questions there already looked at the calculation. Okay, let's continue and talk about the installation part. So we're looking at the ventilation now, and let me just say that for now we're going to look into how to actually do the ventilation part in the EAT program, and tomorrow, depending on how much time we have, we'll look at how to actually calculate this. How many liters per second, and how to actually go around that part, and how much size does the ventilation fit. But today we're going to talk about how to actually do the calculation, how to fill out this schedule in order to get the program to do the calculation. So basically, if we have natural ventilation, check out the help function, basically F1 or the SBI instruction 230. When doing mechanical ventilation, we can often get help, or we get the data from the companies. Efficiency, heat recovery, heating surface, electricity entered are some of the most important part of information. And I'll show you how to do that. Okay, so ventilation strategies, typically dwellings, which is not the project we're doing this semester, but we already did. It's typically, yeah, I would say there are some natural ventilation, but today most of the buildings in Denmark, at least, also dwellings, one-story house will be mechanical. Mechanical extracted or balanced ventilation. And in some cases, we also have hybrid, where there's a mix between those two. It could be mechanical in the winter time and natural in the summertime, or maybe a mix of both in the summertime. When we go to offices or buildings other than dwellings, we have natural. In combination with mechanical, with these buildings today, for new buildings, you could not be, it's not allowed to do natural ventilation in Denmark for offices or buildings that are not dwellings, other buildings than dwellings. At least per se, it's not. I think there are some ways of doing it, but then you need to do documentation that it's actually going to work better than mechanical. But I would say very few buildings in Denmark today go with total natural ventilation. And if you need to do that, I think it is permitted, but then you need to get a special permission to do that. And in that permission, there's a huge documentation part, because, and the reason for that is that natural ventilation in a big building like an office is really difficult to control, and you need to actually do a huge documentation that you're actually gonna make it, or the ventilation is gonna be efficient enough in the winter time. And also, when you're doing natural ventilation, you will have a difficult time achieving the building energy frame efficiency, because natural ventilation also includes that heating up the building in the winter time. You'll 20 degrees air is going to exit the building, and minus 12 degrees during the worst part of winter time will come into the building, and this different temperature difference needs to be reheated by your heating system. There are some solutions you can combine with natural ventilation, such as solar heated walls, where the sun preheats the air before entering the buildings. But this is a very special case, I guess. So we have mechanical, which is typically used, or you can use a hybrid solution. Or basically in the winter and summertime, you combine these two. So and the reason why I stopped is that I don't get why at this. I don't know if it looks like that for you, but for me it looks like this presentation is cut off for some reason. So I cannot see like the top part and the bottom part. I don't know how to change that even. Okay, if we don't see the whole thing, I think I'm gonna, yeah. Let's just, continue.
We can
So
see
basically, sorry? You see?
sorry, nothing. Yeah.
Yeah. So when we're looking at the ventilation input in VAT, for dwelling buildings, typically we see the whole building as one, or one apartment as one zone. But when we're looking at industrial buildings or office buildings, we will have to need to see, yeah, we have to divide the building into different zones. Yeah, let me show you an example of what I mean by zones. I'll just use the example that is built in the 18. So basically, when you start off the project, there's an example of administration building. And if you don't know what the line is, it's basically where you install a program. And there's in that back, there are some examples. The examples is great. This is the house, the dwelling, and there's an administration building, which basically is an example of other than dwelling units. So if you open that one, this is already pre-out done. You can see this as an example. Furthermore, in the also in the I think also in the SBE 213, SBI 213, you can see this. But if you go to examples, you can see the administration building here. This is the example of the administration buildings, which is the data comes from. Basically, it's just two drawings and the facts about the buildings. But what I wanted to explain is that when we look at the dwelling, we see the whole building as one zone, at least, or one apartment as one zone. But the thing about the ventilation for instance, an office building or administration building like this, is that depending on what kind of room we have some different ventilation strategies. A meeting room, for instance, this middle room is a meeting room, and meeting room is a typical normally not being used all day. It's only being used a few hours during the day, probably. But while it's being used, it's really a lot of people inside. And if you have, for instance, a meeting room, let's just say this is a meeting room pointing south, and a lot of people will go in a small area, this room will need a lot of air for when it's being used in the worst case, but during the other hours, it's not going to be used. And that will often want us to pick a ventilation strategy that this room needs big ventilation ducts, a lot of air in the worst case, but most time it doesn't really need it. But this is going to need a different ventilation strategy than the canteen, which basically is where you eat your food and getting. And another one would be the reception. There's going to be one person and a lot of people going in and out. The ventilation strategy is going to be different. There's a copy room, there's a toilet, and etc. And this basically, as you can see, in the ventilation room here, you have the meeting room. You can see it's a one zone. And the reason why they only put one meeting room is because they added both of them in the same area. They have the same ventilation strategy, you can see, for this one as for this one. So there's basically just took the whole area for that one. They have another one for the canteen, for the toilets, for the office spaces, and then for the how do you call it, the reception, and this walkways here, hallways, is another one. So that will be the zones in this room for this building, right? And as you can see, yeah, we'll go back to this one afterwards. Stop sharing. So basically, those are the zones. The FO factor is the utilization of the ventilation tank during work time. So basically, if the FO factor is 1, it means that if we define the building to be running 45 hours a week, it's going to be turned on like this, like you defined, for 45 hours a week. Okay, so Then we have, I'll go back to the schedule and show you afterwards. So basically, Q mechanical, Q stands for the airflow, M for mechanical. So mechanical ventilation in the wintertime. If it's QMV, it's wintertime. Yeah, or QM would be wintertime, QMS would be Q2 or ventilation airflow. Mechanical. Basically, how many liters per square meters. So here we have to know how to calculate these liters per seconds per square meter, and this is something we will do some calculations. The efficiency factor. I don't know. This is a Greek letter. I don't recall. I think it's called nu or something. Basically, it's the symbol for efficiency factor of the temperature efficiency factor for the heat exchanger. It's something we can get from the manufacturer, or else we can get the minimum requirements from building regulations. So we know that this is the lowest number that would actually be there. Ti is the inlet temperature in degrees Celsius in case of heating elements in the ventilation system. So basically, it's a bit weird, this one, because it says what is the inlet temperature. In most cases, it's going to be 18 degrees. But basically, look into the SPI 213 for different cases. Then we have the SEL factor. I can't really get to the bottom of this one. Specifically, electricity consumption for air transport. So basically, SEL factor is it's a Danish one. I think in English it will be SPS, specific. Specific fan power. Where's the SFP? Yeah, I don't remember. Anyway, so this is you could call it a key number for energy usage of the ventilation system. So basically, kilojoules is a unit for energy, and square cubic meter per cubic meter air. So basically this number would explain to us how many kilojoules does the ventilation system use for each cubic meter fresh air that comes from the outside of the building to the inside of the building. And of course, in this sense, you get like some numbers from the manufacturers, or you can look at the building regulation and see what is the minimum requirement or maximum requirement, to be honest. But in reality, the manufacturer can't really control this one, because if you design a ventilation system on a building where you have really long ducts, and you have a really tight ducts, or with small radius of the ducts or small areas, your system in your building is gonna use more energy to get the air out to the rooms. So basically, this is something you as a designer need to be aware of. Typically, this is something that the HVAC engineer will use. But when you're doing this in your project, you also need to be aware of this and use to like rules of thumbs designing. Because I don't think you're going to learn how to calculate this energy consumption, but you need to be aware of it and have some kind of intuition of what we need to do, a small number or a large number. In general, making big calculation following the rules of thumbs we will not talk about tomorrow will help us. Okay, but in practice, you will probably need to work together with an HVAC engineer. Okay. Then we have QNI, which basically is the natural ventilation in the wintertime. And if we have a mechanical ventilation system without natural ventilation, this one is still going to be needed, because if you want it or not, you're going to have infiltration in the wintertime, which you can't control. That was what I talked about earlier regarding the infiltration of the building. So basically, even though you don't want any natural ventilation, you're gonna get it as infiltration because of the height, unless it's a spaceship, I guess. But no building that we're building today are gonna be airtight. So basically, the consequence is that all buildings we build today have some kind of natural ventilation where we can't use the heat exchanger. Then we have the QMW, which basically means mechanical ventilation in the summertime. No, sorry, wintertime. Again, the minimum requirement being 0.3, so we cannot go below that. We're going to talk about this requirement tomorrow. Then we have the QNS, this is the natural ventilation in the summertime. Again, it cannot be below the minimum value for air tightness. And then we have QIN, which is the infiltration in the nighttime, also depending on the air tightness. Okay. How do I change to the next one? Where did my... Oh, there it was. A specific heat fan power, in Danish called SEL, and the VGV is the heat recovery efficiency. So here we can see what the minimum requirements or maximum requirements were. There's something happening there with the graphics. Okay, so this is for residential buildings for public buildings, basically GGB, the recovery factor is the minimum requirement, so often it will be higher, 70 or 75 percentage. And this SEL factor for that we have a VAV, which stands for, and again we'll talk about more about this tomorrow. But VAV is a variable air volume. So basically, this is a ventilation system where it can control how much air is going to come in and out. If we have CAV, it's a constant air volume. So basically, that means when you turn it on, it's going to go, and you cannot control it while it's turned on. It's going to go with a constant speed. Not speed, but constant air volume. So basically constant how much air is going to go in. And then we have extraction system where we're only sucking air out of the building. These are the minimum requirements. So I talked about the blower door tests and the infiltration earlier, but now I just wanted to show you this is also, I want to show you how to calculate the actual infiltration for a building. So we talked about the minimum requirements. The minimum requirements of the building for 2020. This is the formula, and basically for 2010 it was 1.5 for this blower test. In 2015 it was 1.0, and also 2018. In 2020 it's going to be 0.5, and basically the other part of the formula is an empirical formula how to calculate what the infiltration will be. So basically, for the minimum requirements for 2018, basically you can convert this into meaning that we have 0.1 liters per second per square meters in the natural or infiltration loss of the building. Unless we're going for a 2020 or low energy building, it's going to be 0.0. Okay, so these are the numbers that you need to use, these two, depending on if you're building like 2018, which were the same as 2015 or 2020. Yeah. Also, I would suggest going in the SB instruction book, guidance book 213. If you look on the ventilation chapter, you will see some strategies on how these big things should be understood. It would be nice, or a strategy to how to do the zones. Okay. If we have a natural ventilated building, you should only fill out these green parts for dwellings. One second. Yeah. if we have a mechanical, the red parts should be filled out. If we have a hybrid, yeah, these are the ones that should be filled out. And yeah, notice that yeah, depending on if it's a dwelling or not dwelling, see, there's something called a net, which basically means night, and the same is here. So basically, if it's a dwelling, the building doesn't really have a night schedule; it only has a day schedule. But if it's in another building, then it's going to be divided up into. It's going to be divided up into when the building is in usage, like from 8 to 16 or during work hours, and the rest of and when people go home, it's going to run on night setting, and that should also be incorporated into the calculation. And yeah, here again from the SDI 213, some strategies on requirements and how to fill out this. Don't look at that for inspiration. Okay, so I'm just gonna share my screen again, do a quick summation. Now my screen shared. So basically, as I talked about before, all the offices find in the association area. Then we have toilets, and we have copy room, meeting room, and canteen. Basically, this is my zones in this part. So basically, filling up the area. And if we look at the canteen, it says the factor 0.5. Basically, that means that if we go to the administration part, like the main site, you can see that normal usage work hours is 45 hours, and it's from 8 to 17. So when I go back to the ventilation, this means that when it says 1, it's in use 100% of the time of the working hours, so basically from 9 to 7, whereas the canteen is only being used half the time. That means also we're only using these numbers half the time of the year. So basically, that this is while the system is running, it's going to use the energy as described here, and the other part is going to be turned off and only having some small natural ventilation. Okay, so that's the FO factor, like the usage factor. Then we have the QM, which would be the mechanical ventilation part. So for the meeting rooms, you could see that it's pretty high. You can see it's 0.68, and the toilets are also 0.6, so it's going to be pretty high. But if you look at the canteen, it's really high, basically, because we have a high demand for the canteen due to people are eating, and maybe something is going to be there, so it's a local canteen. If we look at the offices, it says 0, so basically that tells me that these two zones are naturally ventilated. And I would just say this is an old example today. You will not be able to build an office building that will be natural. This is not especially needed, and you get like a permission for that, but normally it wouldn't. And it's because of it's a natural ventilator. There's going to be no factor of heat regeneration. So there's no whereas to the meeting rooms and the canteen, we actually get to recover some of the heat that we actually extracted. This will be the inlet temperature. If we don't have mechanical ventilation, it's just going to be 0. Meaning that it's going to be the outdoor temperature. This one will ask whether or not it's either a 0 or 1. So if we have a heating coil, will it be heated by electricity, like electrical fan coil, or if it's 0, it's going to be heated by our main heating, which in this case is a district heating. QN, the natural ventilation. You see these numbers are 0.09. which means that even though we have mechanical ventilation, we still have some infiltration, which we cannot control. It's always going to be there. But for the offices, you can see the numbers are, and the hall is a bit much higher because it's the infiltration plus the natural ventilation that they designed. So you can actually get some ventilation into the room. This is during the night time. So basically, when the building is closed, it's also going to be influenced by the untightness of the building. Then you have the self factor. So basically, this is how much go through meters per second per square meter, whereas this one tells us something about how much energy do we need to use in order to keep this system running per cubic meter air. This is both for the mechanical in the summertime and for the then you have the natural in the summertime. So you can see actually this one, since it has both mechanical and natural, so it's going to be a hybrid run in the summertime, whereas only mechanical run in the winter time. The same with as the canteen. If you look at the toilet, there's no natural ventilation besides the infiltration. But you can also see that this number is constant and it's always running. So these toilets have constant extraction system, but no inlet system. Because there's no, I can see that because there's mechanical ventilation, but there's no heat generation. Basically meaning that it's only going to be extracted air from. During the nighttime, it's also running these two systems, which mechanical systems. So basically this tells me that they're going to run during the nighttime, basically probably because they need to do some night cooling during the winter time. Okay, so this is an example of how you can do this ventilation part. I can see that the time now is like 2 minutes to 12 in Denmark, which means our lecture is pretty much over. I will finish this tomorrow and talk about ventilation, furthermore in general about ventilation, showing you some material, and I will talk a bit more about other parts like domestic water, heat pipes, and supplies. Yeah, so I will stop my sharing and say thanks for today. If you have any questions, you can ask them tomorrow probably. So I'll see you later tomorrow. Okay. See you again tomorrow.
Okay. See you later.
Yes.
Thank you for today's lecture.
Yes. No problem.